Hello guys, welcome to another video on light refraction and reflection. So last time we left off at refractions part 1, which was just an introduction video about what refraction was and how there are so many phenomena in nature which could be explained using refraction alone. So we talked about several things like what refraction is, what are the examples of refractions are in nature, but we couldn't get a chance to look at all these straight. So I thought of bringing you a few examples in picture of these phenomena. So let me show you. See, as you can see this in this picture, you could see on some sort of twig or something, a piece of, I think it's a piece of rod of wood or something. I don't know exactly whatever it is. You could see water droplets hanging upside down, and in the background, which is blurry actually, you could see greenish canopy and the sky, which is white here. But as you can see the placement in the background, the green canopy is at the bottom and the sky is at the upper part, is on the top. But when you view it through the droplets, you could see something different. You could see the green canopy is on the top, whereas the sky is at the bottom. So let me zoom in a bit more closer. See, you can see the green in both the droplets. You can see the same. The green canopy is at the top and the sky is at the bottom. But as for the reality, that's not the case. Okay, let me give you another example where what refraction looks like. See, in fact, this is a rod. This is a straight rod. Could be it's pointed, so it's like a fishing rod actually, not the one with an anchor, but this one is just a straight rod where you throw it at a fish inside the water body to capture it. So it's like a spear. I could call it a fishing spear. That would be more accurate. So when you see, it's not straight from the point where it enters the water. In fact, it is a straight rod, but as you can see, there is a slight bending of the rod. The rod appears to be bent when it is submerged inside the water. And why does this happen? It shows that it is not at the exact depth, but it is a bit more lifted upwards towards the viewer. And this is what happened in the last this is what I was mentioning in the last class about this is what happens to something that is submerged beneath the water. It appears to be at a shallow depth. So this is another example of refraction. So another example where refraction occurs, it's actually not quite common to see this phenomenon. See, this phenomenon is most commonly referred to as the sundogs. During sunrise in polar regions, polar regions means places on earth where it is which is very close to the either poles. So it could be North Pole or South Pole, where the weather is cold and you have snowfall. So in these regions, you can see during the sunrise, the original sun appears to be in the middle, which is rising as usual. But along with them, you could see a hazy halo around the sun itself, and also on either sides you can see two bright images of the sun itself. How could this happen? This is another brilliant example of refraction at work. See, the snowfall actually consists of ice crystals of ice. So crystals of ice is in fact transparent, and these transparent ice crystals, when they are falling from the sky, the light which is supposed to go to the either directions pass through these crystals and bend towards the viewer, and that is how these images appear. If you want any further explanation on these, you can ask me in the comment section. I could explain it to you in detail later. So let me just or if you want, I can just show you how. See, if there is this is the sun, and suppose this is where you view it from, those are your eyes. So light rays from sun move out in all possible directions. See, in the atmosphere, I told you there are these special ice crystals that are falling. So they are between you, the viewer, and the sun. So the light ray which passes through the ice crystal at a 90-degree angle, at a 0-degree angle of incidence, passes straight through it and reaches your eyes, and that is what gives the middle sun image. But other rays which go sidewards actually are not incident at 0-degree, but the angle of incidence is more than 0-degree. So what happens? It bends and further bends towards you as it passes through more and more ice crystals, and that is how the light comes towards the viewer's eyes. And these rays give you an apparent image of the sun here and here. So there is the sun in the middle, and these are two small suns around, which you can see as the halo. The halo appears because it's a 3-dimension, so that is why it appears haloish. So that is what the phenomenon of sundog is. So that was just a follow-up montage to the previous class. So let us go into detailed study of the phenomena. So it is refraction of light, part 2 video. So next I am going to discuss about that previous diagram which I told you was important and will be using throughout. The diagram was the light passing from one transparent medium to another transparent medium. In each remember this, kids, in each transparent medium the light travels in a straight line. So but what happens as the light travels from one transparent medium to another transparent medium? That is the question of the first and foremost question of refraction. What would happen? And as you saw, let me use green. Yeah, a light ray coming from, oh, let me just remove this and use a straight line instead. A light ray coming from one transparent medium, it goes straight until it reaches the so-called interface between the two mediums. So this is, until this point is where the light travels in a straight line, or at least it continues along the same path in straight line, of course. So what happens at this point? Let me mark that point. At this particular point, what happens at this particular point? This point is on the interface. So let me remind you guys, this purple line is called the interface. Okay, so what is an interface? That is, an interface is the boundary between two medium. Let me call the medium in the top as medium 1 and medium in the lower side as medium 2. See, where the light is incident is called the point of incidence. It is given here, and we can call it, say, O, the point of incidence O. Now let me again, the interface is a flat surface. Remember, it is not a line, but it is a flat surface. It's not like whatever I am giving right now is just a sideway view, okay, a view from the side. So don't think that the interface is actually a straight line. An interface between two medium is actually a plane. It's a flat surface. So the light rays, the beam of light comes from one medium and is incident on this flat surface at a point, at a given point, and that point is called the point of incidence. Now next, at the point of incidence, just to study the subject in a bit more mathematical sense, we define a normal to the plane of the interface. We define a normal to the plane of incidence. See, the purple interface, the interface itself is called the plane of incidence. Okay, so let me just write it down so that you don't forget. Interface is actually the plane of incidence. Plane of incidence. It is the boundary between two medium. So it is a plane of incidence. So this is this O, the point O was the point of incidence. It is a point on the plane of incidence where the light ray from one medium is incident. So let me just, don't keep repeating it, and go on ahead and define what a normal at that point looks like. The normal at that point will be a perpendicular imaginary line, a line is perpendicular to the plane of incidence. So this purple line was our plane of incidence, this was our plane of incidence, and then this is our normal, this is our normal, and the normal is actually perpendicular, is perpendicular to the plane of incidence. It is at 90 degree. So normal is just an imaginary line. It is used just to measure the angle at which our light ray, our incident ray, this green ray is the incident ray, is incident at what angle? So we can call it the angle of incidence. So this is what the angle of incidence is. See, at the interface, the light ray, when it is incident there can two main things, two physical phenomena can happen at that point of incidence. And what were those phenomena? If you remember, the light ray could, at the point of incidence, it could partially reflect back to the same medium. It could go back into the same medium. The incoming incident ray at the point of incidence could reflect back if the interface was a reflecting surface. Even if it is not a perfectly reflecting surface, there can be partial reflections. This is called partial reflection because not the entire incident ray is reflected, but only a part of the incident ray is reflected. So a part of the incident ray is reflected, and this angle with respect to normal was called the angle of reflection. So incident ray, like about 20% of the incident ray, say, was reflected. So what happens to the remaining 80% of the light? The 80%, see, this 20-80 divide is not a general thing, okay? Remember that it can vary. It can vary depending on the material. It can, if it is a more reflective surface, then there will be like 60 or 70 or 80% light is reflected. If it is a transparent medium, then obviously the reflection will be less and there will be more transmission. So reflection, the light, if say 10% or 20% is reflected, what happens to the remaining 90-80% of light? It goes through the second medium. It goes through the second medium. Let me use another say color. I could go with yellow. No, I will go with say blue. Yeah, I will use blue. Maybe I should be using a straight line. From the point of incidence, see, it goes to the second medium, but here it won't continue along the same path of the incident ray. It cannot continue along the same path of the incident ray. It will either move closer towards the normal, or it could move away from the normal. See guys, two things can happen. One is that it can deviate from the actual path towards the normal. See, this is the actual path, right? See, as you can see, the incident ray and the light that goes through the second medium are on the same path, but actually this is not what is going to happen. You know, there will be, the light will start to bend at the point of incidence. Either it will go closer to the normal, or it will deviate from its original path away from the normal, or it will move towards the normal. See, these are the two things that can happen. Either it can go away from the normal. So this is also a deviation, right? It is appearing to move away from the normal, and it has deviated from its original path. Let me just mark the original path here. I can mark the original path using some green ray. So this is actually the original path. Let me not use full line. I can just make dotted lines. See, these dotted lines actually represent the original path, but that is not what is going to happen in the second medium. The light ray, I can use blue. The light ray will, in the second medium, will not go in the actual path. It will move away from the actual path. It will deviate from the actual path. It will either move away from the normal. Okay, I'm sorry. it will either move away from the normal or it will come towards the normal. See, the light ray is bent towards the normal. This red line inside the medium, second medium, is also the normal. It will either come towards the normal or it will go away from the normal. So it will be fixed at the point of incidence. So only part which will be deviated will be the one with the x, I guess. Yeah. So it will deviate from the actual path. It depends on the type of medium 2. See, to understand towards which direction it will move, we will have to understand a new quantity, a new physical quantity, which goes by the name of refractive index. So whether will it move towards the normal or whether will it move away from the normal depends on the refractive index of the medium 2 with respect to medium 1. See, let me highlight it again. It depends on the refractive index of medium 2 with respect to medium 1. That is what is going to dictate whether it should go away or come towards the normal. So there is in another way we can refer to this. If medium 1 or medium 2, say, let me just take medium 2. If medium 2 is more denser, see, density here is not the mass density. Density here refers to optical density. Okay, there is a certain feature of a transparent medium, and that is the optical density. If optical density of medium 2 is more than optical density of medium 1, then light will bend towards the normal. So this is, it will appear to go along this path. I mean anywhere between the actual path and the normal. Okay, so it will be at a certain angle, and that angle is this. So the light path inside medium 2 will bend towards the normal if and only if the optical density of the medium 2 is more than the optical density of medium 1. So what will happen in the other case? What was the other case? If the medium 2 has a lesser optical density as compared to medium 1, then the light ray will bend away from the or the light ray will deviate in such a way that, see, this is the deviation, right? So let me just align it properly. See, this was the actual path, but the deviation is this. It will deviate in such a fashion that it moves away from the normal. See, it is moving away from the normal. See, the angle between the normal and the ray that passes through the medium 2 is getting more and more. So it moves away from the normal. So when does this particular case happen? This happens when medium 2 is of lesser optical density compared to medium 1. So this angle has increased, and this angle is actually called the angle of refraction. Angle of refraction. We have 3 angles here, but out of which only we will refer to 2 angles. See, there is this angle of incidence, and then there is this angle of reflection, and mostly we won't be studying reflection here, because which we have studied it in the previous section. So reflection won't be dealt anymore. So here we will be only dealing with refraction, and this angle is very important. It is known as the angle of refraction. So that is what it is. So that is what refraction mathematically is going to look like. Okay, so we are going to study refraction based on these two angles, the angle of incidence, the incoming ray, the angle at which the incoming ray is with respect to the normal, and angle of refraction, which will be the angle at which the deviated ray moves through the second medium with respect to the normal. So these are the two important points here. So what is next? Let me redraw the diagram once again. So we had an interface. Let me draw two separate cases so that you get a grasp of what I am trying to say here. So let me just mark a point where the light ray is going to be incident. See, these are two separate cases, just assume it to be that way. So we have this light ray in first case. So there is an incoming beam of light. We use green again. We have this light ray which is incident at the point of incidence. Let me draw the normal. I could go ahead and use the purple color. So normal should not stay there, but it should align with the point of incidence because it is the normal to the point of incidence. So there is this normal. Let me mark it N. Let me use the same color as of the oops. So we have the normal. So, again let me just say write one more thing, which is this upper part is medium 1 and medium 2. See, in this case medium 1 has less optical density as compared to medium 2. So optical density of medium 1 is less compared to optical density of medium 2. So which one is optically denser? Obviously medium 2 is optically denser. So what will happen to the light ray? The light ray from the point of incidence will not go in the actual path, but will be bent towards the normal. So it will be bent towards the normal. So this is what is going to happen, and let me mark the angles. This was your I and this was your R, angle of incidence and angle of refraction. Suppose now light, let me redraw the normal in the second case. So that black dot was the point of incidence, so let me align it properly. So you have the normal, let me write it to, this is your normal. Okay, now this interface is actually the interface between medium, this is medium 2 now, and this is medium 1. I have switched their places. Medium 1 on the top, medium 2 on the medium 1 on the bottom, and medium 2 on the top. Same features, that is medium 2 is still the optically denser one, and medium 1 is the less optically dense. It is so medium 2 has more optical density in comparison to medium 1. The light ray from medium 2, suppose light ray is coming in this direction, let me use again, let me use the green ray, green color, and mark it its direction of motion. So this is where the light ray, this is the light ray that is coming. Actually, I'm sorry, I should be aligning it more properly. So the light ray should exactly meet at the point of incidence. Yeah, that appears to be still good. So this is the incident ray. Next, what will happen to the light ray in medium 1 as it moves from medium 2 to medium 1? In medium 2, the light ray is now moving in a less optically dense medium. So M1 is optically less dense compared to medium 2. So light ray will make more angle, or will be deviated away from the normal. So this is what's going to happen. It is going to move away from the normal, and as you can see, this was your angle of incidence, and in this case the angle of refraction was this. So we have drawn the two cases separately. I have drawn the two cases separately, and you can see what happens when light ray travels a straight line. Light ray travels from one optically dense medium to another optically dense medium. Obviously, both medium 1 and medium 2 should be transparent. There is no doubt on that, or at least translucent on certain cases. So you should always remember that optically denser materials have higher something that makes the light ray bend towards the normal, and in the case of optically less denser, it moves away from, and that this particular optical density can be measured using the refractive index of the medium. The refractive index of the medium. See, these two mediums could be any two mediums. It could be water, air, petrol, kerosene, alcohol, diamond, glass, sapphire, any of your transparent gems, anything. It could be anything. There is no particular it should be transparent. There is no particular criteria, but it should be transparent, and also the material should be having uniform optical density throughout. It should not be like at some place the material's optical density is more, and in some place it is large. In real life situation, that may happen. The same medium can have different varying optical density. Same medium can have. This is a particular case, okay? So don't think that this is always the case. In most of the situation, the optical density should be uniform, but there are cases where same medium itself may have varying optical density. Varying optical density. Can you explain, can you mention such an example? Let me give it to you. See, we have water, air. These are actually fluids. So fluids have this have molecules less attached and are loosely bound to each other. So giving temperature, varying temperatures throughout the medium can make it more optically dense in one region and could make it optically rarer. See, less optical density means rarer, okay. Denser and rarer, these are two opposite terms. So I will be referring to optically less dense as rarer and optically more dense as denser. See, there are situations where this happens, and that is during hot summer days. This is the road, actually. This is the road. This is the road. This is your road. On a hot summer day, the temperature of the road goes very high, so it gets heated up. It's too hot here. It's too hot near the surface of the road. But whereas the temperature is reduced as we go up. So there is low temperature here and there is high temperature here. See, due to high temperature, the air molecules are more and more farther away from each other. They maintain a larger gap. So their density, their mass density, which converts to their optical density, becomes less. But as we move upwards, the molecules become more and more cold, or the temperature is still low. So what happens? The air molecules are more close to one another as compared to the lower region. So as we reach top, the air is way colder and the air molecules are also very close to each other, which makes them optically more dense compared to what happens in that. So there is this optical density increases in this direction. There is more optically dense, more dense here, and there is less dense, less optically dense. So we could call it rarer instead of less dense. So this is rarer here. Obviously, what happens to light ray as it moves from optically dense to rare? See, this will be the direction of the normal. So it should bend away. It should bend away from the normal. So this phenomenon is actually a very interesting one, and it is called the mirage, which I will be teaching you in the next chapter. But I am just mentioning it here just in order to make you to give you a sense on things. Okay. So there is this particular case where you have now defined that there is this particular case where optical density in the same medium can vary. Now we have built up enough ample knowledge to understand what the laws of refraction are. Laws of refraction. We have the plane of incidence. See, this green is actually a plane. If you look it from the top to bottom perspective, the plane appears to be this, in this manner. See, this is the top to bottom view. This region is the top. So this is the top, and that is the bottom. So this you cannot see the bottom, you can only see is the top part. So this is a plane and you can only see the top part. But what, in all these cases, what did I do was I was looking in this particular direction. So that is why the entire plane appeared to be like a line. So you could just make a sense of how it looks. So just let me sketch back. So this was the plane of incidence, and suppose there was a light ray, an incoming light ray, and that light ray was, say, let me use a different color, a purple would be fine. Yeah, the light ray was incident on the plane of incidence at this point, and now that point marked black is your point of incidence. And what will be the normal at the point of incidence? The normal at the point of incidence will be an imaginary line which stands perpendicular to the plane. So as you can show that this line, this imaginary line called the normal, is actually perpendicular to the plane. See, it is perpendicular to the plane, and this angle, see, this was your incident ray, this angle is the angle of incidence. Now the medium 2 is below this plane of incidence, below the surface, so it is this particular line. Okay, this is the ray which enters the second medium. See, let me you are not supposed to see this much of ray. Actually it won't appear. I mean, it would appear, but still you should just imagine that it is going into the second medium. So this, after extending the normal to the second medium, you can also measure this angle of refraction. So using this figure, using the angle of incidence and angle of refraction, we could set up a law which was discovered by a scientist back in, I think, 15th century or something. I don't remember exactly. A scientist whose name goes by the name of Snell. So let me just write it down. See, there is a relation, there is a law that connects between the angle of incidence and angle of refraction. There is a relationship between these two angles, and that law was discovered by this scientist whose name goes by, I mean, we won't call them scientists. Actually, they were thinkers and philosophers back then. Scientific, I mean, like, people were called scientists only later in the history, actually. So Snell was the thinker or the philosopher who discovered this law which connects a relationship between the angle of incidence and the angle of refraction, and that law is referred to by his name and is called the Snell's Law. Snell's Law. So what is Snell's Law? What does Snell's Law state? Actually, Snell's Law does not directly connect I to R, the angle of incidence to angle of refraction. It actually connects the sign. As you might have studied your trigonometry, or if you haven't, just go and warm up your trigonometry, because Snell's law is actually a law which incorporates trigonometric ratios. So the angle, see, I and R are angles, actually they are angles. So for any given angle we can calculate the sine value of the angles. Okay, so whatever the angle theta is, we can calculate the corresponding sine values. So if you are given angle I, you can find sine of I. You can find sine of I. See, for example, let me just demonstrate it using my calculator. Sine of any angle. Suppose my angle of incidence was say 43. So what will be the sine of 43? Let's see, 0.681. See, there is a corresponding value corresponding to 43. For a 43, the sine value is 0.681, and there is extra terms which we are not considering. It's now for, let me just use another angle. Let me go with say sine of 78. I don't know why am I choosing this. I'm just selecting them randomly. Sine of 78. What is sine of 78? It is 0.978. So also that value, that also has a value. See, we are using angle of incidence here. So whenever I go and plug in a value here, I mean, like whether it is 78 or 43 or even can I go with 90? Yeah, 90 has a sine value, but can angle of incidence be 90? What does it look like? Let me just go back to our board and see what angle of incidence 90 looks like. See, the angle of incidence 90 would look like, so this is your normal, this is your interface, this is the normal. Let me just write it here. This is your normal. 90 from here would look 90 from here looks, what is 90? So it is 90 here. So the incident ray will go parallel to the plane of surface. So will it go to the second medium? No, it will not go. So angle of incidence 90 degree is of no good interest to us. So any angle which is between what is 0 degree? 0 degree will look like 0 degree will be parallel to the normal. So the incident ray will go straight down. Okay, so that is also not of any good interest. So the angle of incidence go there. So the angle of incidence I has a value between 0 degree and must be less than 90 degree. Similar to that, we can have angle of refraction, the value of which should also be I don't know, it might be between 90 degree and 0 degree. 0 degree, it could be, I mean, it cannot be, I think it will be way less than 90 degree. It's mostly way less than 90 degree. So these are the values. So our value which we select for I should be between 90 and 0, and corresponding output value will be 0. So for any values of angle theta, we can find their corresponding sine values. So we can find sine of I, provided some I is given, and then we can also find sine of R, the angle of refraction. Once you have found these two values, if you Snell stated that the ratio between these two angles, the sine of these two angles, see, given any angle of incidence, you put your ray at any given angle of incidence between 0 and 90 degree, okay, and you look at the angle, look at the refracted ray and measure the corresponding angle of refraction. See, I and R are not independent. You give an I, then there will be a corresponding value for R. You have a given I angle of incidence, and then corresponding to it there will be a angle of refraction. It is not that R is independent, it cannot be anything. For a given I there is a given R, and so if you take the ratio of the sine of the I and sine of the R, this ratio will be constant, will be a constant for the given set of medium, for given M1 and M2 mediums, for a given set of media. So this is Snell's law. Snell's law states that the sine of the angle of the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for a given set of media, for a given pair of media. That is what Snell's law is. Snell's law itself makes one part of the law of refraction. So just like in the case of reflection, we have a reflection, we have laws of refraction too, and these are the two laws of refraction, out of which we just studied the Snell's law. This was your Snell's law. So law of refraction. So there are two sets of laws in the laws of refraction of light. Obviously we are studying about light. The first law goes, and you might even remember it in the law of reflection. It's in both cases it is same, but instead of reflected ray they are using refracted ray. So what is the first law? What was the first law? First statement is the incident ray, the refracted ray, and the normal to the interface of the two transparent medium at the point of incidence all lie in the same plane. Which plane are they talking about? If you remember, in the class I have told you which plane it is. See, in this case, let me just show you which, let me just remind you which plane it is. Let me just remind you what it is. What was it is? What was this plane they were referring to? See, let me whichever device you are watching in, it has got a screen, and that screen is the plane which they are referring to. So this rectangle you see is a flat surface on your screen. Your incident ray, okay, your incident ray, the normal to the point of incidence, which is this, and your refracted ray, all these three lie on this rectangular plane. So they are all flat on this, they are flat imprints on this plane. So that is the plane that they are referring to. Okay, all right. So that is what law of reflection is. Now let me move on to the index of refraction, or the refractive index. So the index of refraction, this is a very important topic, and will comprise of many mathematical type of questions in your board, for your board exams. So refractive index. So refractive index. See, roughly speaking, refractive index actually refers to the optical density. Refractive index speaks of optical densities, optical density. Refractive index refers to optical density. Refractive index is about optical density of two media compared. See, so how do you measure refractive index? So refractive index is actually a number which gives how much a given medium is optically dense with compared to the second medium. So how can you define refractive index? So it all goes to the fact or the reason for why refraction actually exists. Why refraction? Why does refraction occur? See, let me loosely state it. Refraction actually occurs because of several other reasons, but the exact reason for this refraction at the point of incidence is a bit more complicated, because you will have to know the electromagnetic nature of light to actually really comprehend what refraction means. But still, I can for your level I can say why this occurs. Refraction occurs because of something known as the speed of light. Something known as the speed of light. Speed of light. You might have known the light travels at a very faster pace. The speed of light is way faster than one can imagine. That is why when you just switch on your light, instantly the light spreads throughout the room. It is not that when you turn on the light and the bulb takes for you to see the bulb, it does not takes you 5 minutes, not even 1 second. It happens within a very tiny amount of time, but it does takes time. It is not that it is infinitely fast. There is a limit to the speed at which light reaches your eyes, and that speed depends on which medium the light is traveling. If the light is traveling in vacuum, if the medium is air or vacuum, the velocity of light will be v 3 into 10 raised to 8 meters per second in SI units. So what is 3 into 10 raised to 8 meters per second means 3 followed by 8 zeros. 8 zeros meters in 1 second. So what does 8 zeros look like? This is 1000, this is million. So it is like 0.3 billion meters per second. 0.3 billion meters per second. Or if you are an Indian, you could just no, you could call this like this is 1000, this is 10,000, this is lakh, 10 lakh, I think this is crore. Okay, let me just convert it to kilometers per second, so that would be better because it is becoming more confused because I don't know anything beyond crore. There are 100,000 crores, but there are no other denominations. So if I call it to be in kilometers per second, then I will call it 3 lakhs kilometers per second. So that is how fast the speed of light is in vacuum. 3 lakhs kilometers it is. But the light does not travel so fast in water or kerosene or alcohol or maybe glass. It has an entirely different speed. Even I could go ahead and say that the speed of light is less in water than in vacuum. The speed of light is less in glass than in vacuum. So what is the reason behind why does this happen is it's a very complicated thing, but still just understand this point that speed of light is not 3 into 10 raised to 8 meter per second in water. It is less than that. Even I can go ahead and say the value. In water, the speed of light, I can just write a subscript W, which means water. Speed of light in water is around 225,000 kilometer per second, and speed of light in glass is around 200,000 kilometer per second. See, compare this value with the speed of light in vacuum. Speed of light in vacuum was how much? It was VV. See, instead of VV, I am going to use a standard notation, which is C. The C, speed of light in vacuum, is 300,000 kilometer per second. So it's 3 lakh kilometers per second. See, this C, why have I used C here? C actually is because of historical reasons. C stands for a Latin word. I mean, this is not important for your exams and all that, but just learn it. C stands is a Latin word called celeritas. Okay, it's a Latin word, celeritas, which means swift or fast. Swift means fast. Okay, so celeritas refers to fast. So that's why C is in particular used to refer to speed of light in vacuum. In other cases, I will be going ahead and using V, small letter V. So this is as you can see, the speed of light in vacuum is different from speed of light in air, is different from speed of light in water, and it is different in the glass also. So in each optical medium, the speed of light changes or is different. See, it is you should never assume that there is an acceleration going here. Light never accelerates. The speed of light in a given medium will remain a constant provided the medium's refractive index does not changes. Also, see, you can see if there is vacuum here, vacuum, and this is your interface, and there is water. As light comes from vacuum to water, at this point there is no acceleration. So there is no acceleration, I mean, so there is no deceleration. The speed changes and it is indicated just by a deviation in the path. So there is no acceleration. Just don't think that since the speed has changed from 3 lakhs to, say, in water it was around 2.25 lakh kilometer per second, it is not change, it is not decelerating or it is not accelerating. Okay, there is no acceleration. It happens at the point of incidence is that there are processes happening which absorbs light and re-emits light at this speed. That is the only best easy explanation I can give to you, but there is no acceleration, that I can guarantee. Okay, so there is also one special feature. When light travels from say vacuum to water, the refracted ray bends towards the normal, deviates towards the normal. Okay, again coming to another case, when light goes from water to glass, let me draw a normal here as well as in here. So when light moves from water to glass, what happens? The light moves away from the normal. So if I go back to the slide where the speeds were given, so these are just a few examples. Okay, so as you can see, if when the light moves from a medium, oh actually I'm very sorry, okay, I will be cutting down that. Okay, fine. See, when now when light moves from glass to water, the light ray, let me draw the normal here, the light ray moves away from the normal. Also, for vacuum to glass, light moves towards the normal. For water to glass, again light moves towards the normal. And from glass to vacuum, light moves away from the normal. Similarly, for water to vacuum, light moves away from the normal. So just why does this happen? I mean, like, this happens and the reason behind, or at least we could just refer to a pattern. We can see a pattern here. Speed of light, when light travels from when light travels from a medium of speed of from a medium where the speed of light is higher, when the speed of light is higher in one medium and speed of light is low in to a medium where the speed of light is low, it's a slow where the light travels slower, the ray bend towards the normal, and the case where, let me just pick a new page, and in cases where when the light travels from a medium where its speed is low to a medium where the speed is high, the ray bends away from the normal. Now this is an open question for you guys. I will be continuing the rest in the next part, where we will be properly defining refractive index. So let me ask you a question. This is an open question. You will have to find an answer to it. You might have seen such a pattern. I'm sorry. You might have seen such a pattern when you went on ahead to define the optical density, and then you found out that okay, let the question be, the question is to find whether optical density connects to speed of light in a given medium, for a given medium. Is there any relation? Like if optical density is higher, what will happen to the speed of light? If optical density is lower, what will happen to the speed of light? So this is an open question to you guys. You need to find the answer to it. I will be back again with the proper definition of refractive index in the next class. I wanted to say you just find these two, find the connection between these two, then we will continue the rest. Thank you very much.